Welcome to the Chapter 4, Section 7 podcast. This is on graphs of motion. We've looked at the relationship with a freely falling object, and now what we're going to look at is graphs of this object. Rather than looking at tables and equations, we're going to actually graph it out to see what it looks like. So, like I said here, equations and tables are not the only way to look at it. We're going to look at it using graphs so we can visually understand this. So here's the speed versus time graph, and here on this axis we've looked at the speed for freely falling object, and here it's over time. And as you remember, for freely falling object the velocity increases 10 meters per second for every second. So you can just see it once it's gone from 0 to 10 and then 10 to 20. I often hear of best fit curves. So the curve that best fits the points in this line is a straight line, and this relationship is a straight line. And so, like we said, for every second there's a 10 meters per second increase for every second, and this is called linearity. You can see it's a straight line, and and because they dropped it from rest, the line starts at the origin. Right here, that's the origin. V and T are both 0 there. And you see if we double the time, let's go from 1 second to 2 seconds, your velocity will go from 10 to 20. So if you double it, you double the velocity. If you triple the time, you triple the velocity, etc. Now we call this direct proportion. We say that the time and speed are directly proportional to each other, and I'm going to contrast that later on. Now, because this is a straight line, the slope is constant, and that's the vertical change divided by the horizontal change for any part of the line. Another way of, you probably heard this phrase before in math, the slope of a line is the rise over the run. Here's the rise, here's the run. So what you would do is divide any change going in the vertical direction by any change in the horizontal direction. So for every 10 meters of vertical change, you're only going to have one change of 1 second horizontally. So what we would do is divide 10 meters per second by 1 second. What do we get? 10 meters per second squared, which is the acceleration due to gravity. And we can see that no matter where we do this on the graph, we're going to get the same result, 10 meters per second. So we say that the acceleration is constant, and that's what this straight line represents, is that the acceleration is constant. Now if the acceleration were greater, then the slope of the graph would be steeper, meaning the line would be more like that. That would be a steeper acceleration. That might occur somewhere like on the planet Jupiter. On the moon, our acceleration probably would be something closer to, say, that, because there's not as much gravity on the moon. So let's look at distance versus time graph. And excuse me, in this case, we're going to plot distance on the vertical and time on the horizontal again, and what we end up is a curved line. This line is a parabolic. You can see the line curves as opposed to that straight line that we saw with the velocity over time. Now, this relationship, we said that the relationship between velocity and time is linear. This is non-linear. It's not a straight line. The relationship is quadratic, and the curve is parabolic. In other words, if we double t, we don't double d, we quadruple t. That's a quadratic equation. And then what it ends up is a parabolic curve. It's a quadratic relationship, but parabolic curve. And what this, and as you can see, is as distance doesn't depend on time, it depends on time squared. So that means every time you double the distance, you're going to quadruple the time. I'm sorry, every time you double the time, you're going to quadruple the distance. Now, the other thing you have to remember is that the slope for this curved line is different at different points. If we look at the slope, let me change my pointer. If you the slope here looks like that, but the slope down here looks like that. And you can see the slope up here is even steeper. So you can see the slope changes as you go throughout the curve. So it changes from one point to the next. So, and it's this slope of this curve is the speed. It's the rate at which distance is covered by time. The way I always remember this is what's distance divided by time? It's speed. That's how I remember what the slope is. So the slope becomes greater as time passes. You can see the slope's getting greater here, which shows that speed increases as time passes. This makes sense because the object's accelerating. So as time goes on, the speed is going to get greater, so the slope of our distance versus time graph is going to get greater. So what does the slope of a speed versus time graph represent? In this case, the slope of a speed versus time graph represents speed per time, or our acceleration.